And you have a logic of AND OR logic. We accepted, but here 2 units. NAND is called Academy. I will help you. Sainath, Deepanjali, Rushi, my sister, good evening, good evening. So let's start the session. So we are discussing combinational circuit. Yesterday class we discussed half adder, full adder, half subtractor, full subtractor. Now let's see the application. Okay, so let's move further. Namaste Vivek. 4-bit parallel adder or ripple carry adder. So the next topic. Good evening, Akshat, Namaskaram, Eddie. So this is what we are going to discuss now. Right. Good evening, maybe. Yes, this is only. So now good evening. Very good. So let's start this. Suppose I have 4 full adders like this. Full adder 3, 2, 1, and 0. So I want to make a 4-bit adder circuit. You know, one full adder can add 3 bits at a time. So I have a 2 4-bit numbers. I want to add them. For example, I have, good evening, Ravi, first slide only. A3, A2, A1, A0. I have a 4-bit number A. I want to add these to another 4-bit number B3, B2, B1, B0. So what is the original procedure? So you will be adding this A0 and B0. You will be getting sum. You will be getting sum, and what happened here? Yesterday also same. Yeah. Just give me a minute. Let me okay. So it's working. You will be getting sum S0 and carry will be given next. Good evening, Aman. You will be getting sum and carry will be given next, and you will be getting sum and carry will be given to the next. Then you will be getting sum and carry. So this is how you will be doing your additions, right? Suppose you want to do a 4-bit addition. This is the process to do the addition. Now please listen here. So I want to perform this operation using these 4 full adders. Using these 4 full adders, I want to perform this operation. Let me do this. You give the inputs A0, B0, A1, B1, A2, B2, and A3, B3. You will be getting sum and carry. Carry is to be taken and added to the next state. You will be getting sum and carry. Carry is to be taken and added to the next state. Okay. So every stage you will have the two outputs, sum and carry. So here, now listen, this is your C naught, A naught, B naught. C naught is the first carry. Generally you make it as 0. Okay, initially no carry is there. A1, B1, A2, B2, and here you will be giving A3 and B3. So now what you get is sum S1, sorry, S0 and the carry C1. The carry C1 will be given here. First you do the addition, you get the sum and the carry. Yeah. So now here you will be getting sum and carry. Here also you will be getting the sum S2 and the carry to the next state C3. This C3 will add these three and you will get the sum S3 and the carry C4. This is how it will perform the addition. First A0, B0 will be added, sum and carry, and sum and carry, sum and carry, and again sum and carry. This is how it will perform this addition. This is what we call 4-bit parallel adder or ripple carry adder. Why it is called ripple carry adder? Here carry is propagating from one stage to another stage like a ripple. That's why it is called ripple carry adder. Is it clear what I'm saying? Here carry from how it is performing 4-bit addition. You give A3, A2, A1, A0, A2, AB2, A1, B1, A0, B0. Then first carry is not there. It will do the addition, give the carry to the next stage. Then it will perform its addition, give the sum and carry. It will perform this addition, it will give sum and carry. It will perform this addition, it will give sum and carry. Please understand that. That's why carry is propagated from one to another like a ripple. That's why it is called ripple carry adder. Is this point clear? Okay. Now, okay, fine. Now listen here. Now one more question, one more thing. Here you observe, once you perform this addition, carry will come. Until this carry comes, you don't get this sum and carry. For example, if this first here this comes at 20 seconds. For example, just assume it comes at some 30 seconds. All inputs are already applied. So at 30 you are giving this. Before 30, what is the output here? Will this adder start at 30 or before itself it will do its job? No output. Listen here. Adder don't know whether you give carry at 30 or not. It doesn't matter. Before also there will be some output. There will be some output which is based on A1, B1 and already present C1. Please understand that when you apply A3, B3, A2, B2, A1, B1, A0, B0 at time t equal to 0, at that time already based on the available values it will do some addition. Okay, but at t equal to 30 original input is applied here, that will be added and then you get again new output. That will be before getting this new output there will be some intermediate or transient outputs always. Please understand that. Because the adder don't know when you are giving carry, it will do its job always. Okay, when you apply A1, B1 itself, it will do its job based on its C1. Even you change the C1, then it will change its value again. Okay, suppose here to perform this addition, I need to wait for this carry, then this carry, then this carry. Like that, if this length is getting increased, what is the disadvantage? You understand my question? When I increase the length, I need to wait for more and more time. That increased delay, propagation delay will be increased. That is the disadvantage of this parallel adder or ripple carry adder. Okay, the delay will be increased with increase in the number of bits, because the carry input in the present state is depending on carry output from the previous state. So delay increases with increase in the number of bits. That is one disadvantage with this circuit. And another case, listen here. What is the meaning of this 4-bit? Because it is adding two 4-bit numbers at a time, it is called 4-bit adder. If you want to make 8-bit adder, what to do? How to make 8-bit adder? Just take similarly 8 adders and it will do, or 4-bit adders and cascade them, you will get 8-bit adder. Yes, okay. So in computer, you know, in your computers, you will say 32-bit processor, 64-bit processor, like that you will be saying, yes or no? What does it mean? It is generally called as the processor data handling capability. That is a data bus size, people say, or ALU capability only. Okay, so it can perform 32-bit addition at a time, you can say one way. 32-bit, it can handle data of 32-bit at a time. Not address bus size, it is only data bus, Sura. Okay, so it can perform 32 bits, so it will be having 32-bit adder in that case. Okay, why are you worrying about Aditya ripple carry? We are discussing this. Let me complete this and then we'll go to the next topic. Okay, Aditya. So you have still using 8-bit processor, Aditya? No, please listen. This is not feedback. This is one output is connected to the input of next. People, very good. It is not feedback. It is cascade. Yes, Samira, your operating system is able to capable of doing 32-bit operations at a time. It can handle 32-bit of data at a time. Originally, we say by data bus size or ALU capability. Okay. Now, listen here. What is the total delay in this circuit? Total delay in this circuit is equal to n times full adder delay. N times the delay of each full adder. Will you accept it? So 1 delay for this, 2 delay for this, 3 delay for this, 4 delay for finally getting the output. N times the full adder, each full adder requires some x. So you can say the total delay will be an x. Yes or no? It can also be given by n times 2tz if full adder delay equal to delay is taken as 2 times tz. Why? Because in the full adder, what you have, you know, what you have yesterday class. Each full adder internally contains how much? One AND followed by OR or two XOR gates, which requires 2 gate delays. What is tz here? Gate delay. What is the TFA? Full adder total delay. One full adder delay. Okay, because it is internally 2 level, you can also take n times 2t. Okay, internally it is 2 level. If the examiner gives that, okay, he will tell you what to use. Okay, internal circuit, he will specify it. We should not assume it. Generally, he will specify. We'll see the problems. Next, listen here. You can also write total delay is equal to n minus 1 times sum plus maximum of TS and TC. Sir, what is this TS TC business? I will tell you. What is TS? It is the propagation delay for sum of one full adder. What is TC? It is the propagation delay of carry of one full adder. What is TS? It is the propagation delay of sum for one full adder and propagation delay of carry for one full adder. In that, please understand this. You should wait for this carry, this carry, this carry. How many carries you need to wait, man? Tell me. First carry, second carry, third carry, 3 carries. Can I say 3 carries is nothing but n minus 1? Can I say 3 carries is nothing but n minus 1? Yes. So n minus 1 times you should wait for carry. Okay. So I'm sorry. Very good. N minus 1 times to carry, and listen here. 3 times I got carry. Last time I should wait for both of them. I should wait for both of them to get the final result. So in that case, what I will do is I will take maximum of these two. Whichever takes more time, that is my delay. Whichever takes more time, that is my delay. So maximum of TS and TC. Okay, then you may have the doubt, sir. You are considering only this part. What about these sums, sir? Don't worry. Please listen. You are waiting for this carry, this carry, this carry. Finally, you are waiting for its sum and carry also. By that time, these sums already appears. Okay, when you wait for this sum for which you are giving the carry late, by the time you get this sum, already these are ready. These people are already ready because you are waiting for maximum of sum and carry. So is it okay? This formula for total delay is nothing but very good, important formula. Then you got around 3 times question on this in 8. N minus 1 times TC plus maximum of TS and TC. Okay. So let's move further. Similarly, previously you considered whole full adder. You don't, please actual sense listen. Yes, people, I will explain. Previously you considered total delay of this whole full adder. But what I am saying is the second case is you get sum and carry, but you need not wait for sum. Carry comes. This process will proceed. This carry comes now, it will not wait for this sum. This process will give you right answer once this carry is valid because already A2, B2 are waiting. So you need not take whole full adder delay into consideration for these 3. What you need to consider is only carry. Is it clear, people? Only carry you should consider, that is sufficient. Okay. So to implement n-bit parallel adder, we need how many full adders? Okay, that's why we took maximum, na GP. We need originally n full adders, or you can also do this by n minus 1 full adders, and first bit you see, first bit don't require 3 bits addition. Here 2-bit addition will also do my job because this carry input is assumed as a 0. Okay, so you can say 1/2 adder. So new students, if you have doubt, please ask. Don't worry about it. Okay, some people may already know it. Don't worry. No, please listen, Asif. Even this TS, for example, your TS is 80. Okay, your TC is only 5. You complete this 15. Okay, now you again waiting for 80 and 5. Which one is more? Tell me, yaar. You are waiting for 95. This 80 is already gone. Okay, Asif. You are already last phase waiting for sum and carry may maximum. By that time, remaining sums already comes. Okay, that last point line here, you observe here, last maximum of TS and TC. That's all, GP. Okay, maximum of 520. You will wait for 20. Okay, so where we are, n minus 1 full adders and 1 half adder. You know, 1 full adder is equal to how many half adders required? 1 full adder is equal to 2 half adders. So, and OR gate also required definitely. So, 2 times half adders. So, plus 1 half adder. So, what is the answer? 2n minus 2 plus 1. 2n minus 1 half adders. This is a number of half adders per n bit parallel adder. Okay. Don't worry, GPA. Don't worry. Wait for some time. I will explain with the help of example again. Don't worry. So just wait for 2 minutes. Your doubts will get clear. Don't worry about it. I already know you will get this doubt because by this sums will come or not. That doubt will be there. Don't worry. I will clear that. So this is about your ripple carry adder. Yeah, I just left that OR gate. I mean, if examiner asks you, you should say that n minus 1 OR gates also. Okay, originally you require OR gate also. Only half adders, how many are required is 2n minus 1. Definitely OR gates are required. Any issue? Okay, okay. So now come here. Just go through these points. These points already I have given. We can implement 8-bit parallel adder by cascading to 4-bit parallel adders. Next. I already told you, Sushil, just wait for some time. Since carry is propagated like a ripple from one adder to another, okay, it is also called ripple carry adder. I told this point. Since carry input in the present state is depending on carry output from the previous state, delay increases with increase in the number of bits. This is the disadvantage here. We can overcome this disadvantage by using the next adder which we discuss is look ahead adder or look ahead carry or carry look ahead adder that we discuss next. Just wait for some time. Aditya, you asked me also that just wait for some time. Next we'll be discussing. These points already we have discussed. I just kept it so that your notes will be better. Okay. So if you download this PDF also, it will be a good notes for you. No need to worry about it. Now, as so many people ask me that doubt, let me clear that doubt. Before that, let me do one question to give the feel. Adder don't know whether it is signed or unsigned, Ganesh. I don't know whether you attended my previous classes or not. Adder don't know whether it is signed or unsigned. Whatever you do, you give, it adds. You should know whether you are giving signed or unsigned. Adder job is to add only. The data you give, it will add blindly. So this everybody knows it. Aditya, why you are that much hurry? I thought of conducting poll so that I will get 100%. What happened to you today? So your answer is 2m minus 1. To add two m-bit numbers, it's a previous IES question. Okay, the required number of half adders is 2 into m minus 1, not 2 power m. So some people still have that doubt in the delay. Don't worry, just give me 1 minute. I will clear that part now with the help of the question coming. Okay, so let's do the question. What's happening? I think so many biryani lovers are there in the class. So let's do this question and let me prove that formula also with all clearing all your doubts. What people, you are staying in Hyderabad or what? One minute, please. Okay, so let's do this question. In the logic circuit shown in the figure, if in each full adder sum requires 40 nanoseconds, carry require 20 nanoseconds. We have two questions. First one is total delay. Second one, addition rate. You need to find this. Okay. Yeah, you can stop that biryani business. Come here. So this is the question given. Okay. So what happened here? You are attending my class. You know the conditions. Why you are commenting the answer? Do you have any urgency to give the answers, or you have any marks for that? If a new student gives it, that is a different issue. Everybody in the class should be able to learn. Okay. I don't want your answer. Ganesh, you don't understand what I'm saying. Please see it. Your adder don't know whether you are giving signed or unsigned. You take it will do the addition same way. Addition process is same. How you read the result, it depends on our application. Okay, how you interpret the result. Okay, that is in your hands only. Adder will do normal addition, whether it is signed or unsigned. Addition process is same only. It will do that only. You don't know whether you are giving signed number or unsigned number. It doesn't matter for it. Okay, result will be same. Then how you interpret, that is depends on the end user. Okay, let's come here. Okay, so why are you worrying, Sushil? First, let me complete this, then I will come to addition rate. Then I will explain what is the meaning of addition rate. What happened here? Today, you people are behaving differently. Something different. What happened? You know, I will explain anything. Okay. लॉकडाउन इफेक्ट चल रहा है क्या माइंड पे? No. I will explain. Okay, this is the question given. So in the logic circuit shown in the figure, each full adder requires 40 nanoseconds and carry requires 20 nanoseconds. What is the total delay? What is the addition rate? Both we will calculate it. Don't worry. So firstly, take this C naught is equal to 0. Very good. Very good. Listen here. Just come here. Okay. Firstly, please listen. Direct formula. Total delay equal to, what is our formula? N minus 1 times Tc plus maximum of Ts comma Tc. So direct formula will give you N is how much? 4 minus 1 into 3 plus maximum of 40. So what is 3 here? Carry delay is 20, 40 comma 20. It is 60 into 60 plus 40, which will give you 100 nanoseconds. Okay, very good. Most of you got the right answer. Now come here. So those who have doubt in this delay formula, now it will get clear. Just understand carefully. At time t equal to 0, you applied A3, B3, A2, B2, A1, B1, A0, B0. Okay. So at time t equal to 0, you have applied this A and B. Then at what time you get this sum? At what time you get this carry? It is S0 and C1, S1, C2, S3. 1 minute, C3, S2 and C3, S3 and C4. Okay, you tell me you have applied at time t equal to 0 all A naughts. First tell me only S0. Don't say anything. Tell me this part. At what time you get this sum? Everybody, 40 nanoseconds. At what time you get this carry? 20 nanoseconds. Now you observe, sum is coming at 40, carry is coming at 20. So at 20 nanoseconds, your carry is ready. A1, B1 already ready by 0 itself. So at 20 nanoseconds, your carry is ready. Will it start its addition or will it wait for this sum? Will it wait for this sum? It will not worry about this sum. It's carry coming. It knows only carry ready. Okay, start. So at what time you get this? At 20 you applied the last input, na? 20 plus another 40. What is the answer? 60 nanoseconds. Again at 20 you applied, na? So at what time you will get this carry? For some it is 40. For carry 20. 20 plus another 20 is how much? 40 nanoseconds. Now come here. At 40 this fellow is ready. You don't mind about the remaining sums. Carry ready. Okay. So you get this sum here. What is the sum you will get? 40 plus another 40. 80 nanoseconds you will get this. Shifting issue. 1 minute. Just wait. One minute. Yeah. Okay. Now at 40 you applied this. At 80 nanoseconds you will get this. Again. At 40 you applied now 40 plus 20. At what time you will get this? 40 plus 20. Every input plus 20. 60 nanoseconds. So you applied this at 60 nanoseconds. At what time you get the sum? 60 plus 40. How much? 100. And at what time you will get this carry? 60 plus 20, 80. Now out of all the available, final fellow, who is this lazy fellow who will be coming at the last is this man. By the time you get this sum, all are ready. Okay. So because for this lately we give the input. By the time already we have given these inputs early now, so they might be ready already. Now those who have the formula doubt in the delay, now ask me. So 3 times you should wait for carry. 3 times you should wait for carry. 1 time either sum or carry, which takes more time. By the time already these fellows are ready because they wake up early. Okay, fine. Thank you. Right. So let's do your second part. Addition rate. What is addition rate is now, I hope so many asked me, number of additions per second. Very good, Aditya. Number of additions per second. That is what we call addition rate. How many additions are getting performed in 1 second? If you say bit rate, what is the meaning of bit rate? Number of bits transmitted in 1 second. Now, listen here. One addition requires 100 nanoseconds, that is 10 power minus 7. So in 1 second, how many additions? 1 by 10 power minus 7. That is 10 power 7 additions will be performed per 1 second. That's all. Okay. So for example, one addition requires 0.5 seconds. One addition, for example. Okay. In 1 second, how many additions are performed means everybody say 0.5, one addition, sir, two additions will be performed. How to? Actually it is 1 by 0.5. What is your doubt, Harsha? I didn't get. Is this point clear? How you did this? One addition requires 0.5 seconds. In 1 second, how many additions can be performed is 1 by 0.5, 2. Same way here, one addition requires 100 nanoseconds, 10 power minus 7 seconds. So in 1 second, how many this kind of additions can be done? That is the question. Okay, your computer time 1 second is available. How many additions you can perform? Now in this question it is only for this question, Samira. For this figure in this question only. Okay. Megahertz generally we say it for cycles per second. Okay, here additions per second. Better to keep it as additions per second. You can say it is a 10 power 7 as the frequency. Okay. In one sense you can say, okay, but originally we should say it as number of additions per second. You want to calculate bit rate. Bit rate is given as your computer speed 128 kbps. Why don't they say 128 kilohertz bits per second? Similarly here, additions per second. Someone asked me some doubt. I don't know what happened to him. No reply. Wait. Harshvardhan, please ask your doubt again. What is the doubt? Okay. So everybody clear with both the questions? Both the questions clear now? Very good. So all doubts are cleared. So let's move to the next one. So just wait. Okay. Don't comment your answers. I will give you time. Previous gate question. No, 100 nanoseconds is not small, man. For computer, it is matters. Your computer, you are giving this input immediately. You are expecting the output. Whatever big addition you give to calculator, will you wait for 1 second? You want your results instantaneously. So delay should be as low as possible. Okay. Even nanoseconds, picoseconds, everything matters for us. If you go for as much faster as possible, that much required according to your particular operation. So you are seeing only this is 16, this 4 bit. Suppose this kind of are cascaded, then your delay increases now. So delay should be always as minimum as possible. And I am not worrying you, your examiner is worrying about it. And one more thing is, examiner worries generally when there is a real-time problem. Okay, so just go through it. I will give you the options. Just first go through it. It's a previous gate question. You have a 16-bit triple carry adder realized using 16 identical full adder as shown in the figure. The carry propagation delay is 12. Some propagation delay is 15. The worst case delay in the 16-bit adder. Please understand this line. What we are calculating here is worst case delay. It is not the delay in every case. Some cases maybe you are adding 0 0 only. Already, please listen. Some cases carry is already 0. It may be at 0 1 something. It may give 1 no carry. This is already not present now. It may not take extra time. So what we are calculating here is the worst case, worst possibility. We don't know every time carry may not generate now. You know that. Sometimes carry may not generate, sometimes carry may come. We don't know that. This is what we are calculating is the worst possibility. Okay, this formula, whatever we have. Okay, in any case, the delay is generally calculated for worst case. Worst means highest. Nothing specified, always we calculate worst only, Samira. So let's start the poll. Okay. Very good. Most of you given right answer. So Manjunath, Abhinay, Amitabh, Suraj, Abhijit, Mohan, Sagar, RK Singh, GP, Abhineet. So the right answer is 195. This is very simple. No problem. What is the formula here? N minus 1. Where is your n here? 16. So 16 minus 1 into carry delay 12 plus maximum of 15 comma 12. That will give you 195. Right. 15 12 is 180. Maximum of 15 and 12 is 15. Answer is 195. Is it okay? Why some people opted for none, I don't know. Maybe they have not calculated this mathematical part. So please see here, any doubt, please ask. N minus 1 times carry, maximum of sum and carry. So shall we proceed further? Okay. Yeah. Right, Sumit. So I will give you one homework for today. Tomorrow we discuss it in the class. Worst means highest, Ajit. For any random input, it will not be more than that. You are ready for the worst case, means it will not happen more than that. This is your homework. Give a try. Okay. This is not worst case. Here he gave one input. For the specific input he is asking. Tomorrow we do it in the class also. You just give a try for today's practice. Okay. So I'm not saying, I'm just giving a small hint only. Okay. So these two bits, these two are to be added. Each full adder is internally implemented like this. Because you people are little lazy because these many lines you are not interested to read it. No. Read completely. Originally, you need not wait JP, but for the worst case delay, we assume for that also we'll wait because you don't know whether it is 0 or 1. Here, if it is 0, okay, you need not be added. That you analyze. Tomorrow, anyway, we do it. Just your analysis is also important, so you can try. Well, in this case, yeah, this is the worst case means maybe not in any for the any other input answer may be less than that. For example, you try here, what is the carry delay? You try here. This example is given like that. Here at home, you try the worst case possibility, and for this input, how much it is taken. One simple way, Sushil, if it is 0 or 1, forget it. If already at 0, after addition also you get 0, no hazard occurs in between. Need not worry about this delay. Already at 1, okay, after addition also 1 without any hazard, then also don't worry about this delay. Okay, at any case, anytime, same rule. So this question you try as a homework. Tomorrow we do it in the class. I'm giving you so that your analysis skills also will develop. So next question. Similar to adders, you can cascade subtractors also. Yes, Sushil. So this question, I will give you the options. Don't again, some people are hurry. Please wait. I will give you options. Okay, ready? I will start the poll. The circuit shown in the figure is having a 4 boxes. Each is described by PQR. Outputs are Y and Z. Y equal to P XOR, Q XOR, R and Z equal to something given. Okay. Last option is P minus, Q minus, R. Not, I'm sorry. So shall we start the poll? Just listen. Earlier we taken adders. Here we are taking subtractors or adders. You check it and what is the condition you should answer. Start the poll. Yeah. Right. The poll starts. Very good. So you can see Mohan, RK Singh, Deepanjali, Suraj, Arun, Ashish, Deepak, Sura, Amitabh, and Aman. So listen here. Let me do it. Let me do it. Don't worry. Firstly, tell me the point here is A XOR B XOR C. It is in this format only. Now here it is in the form of A bar B plus A bar C plus BC. You tell me, is this in the form of AB plus BC plus CA or A bar B plus A bar C plus BC? First format or second format? Because he don't say whether it is a full adder and full subtractor. You just see the figure and tell me it is in the. This is like your sum and difference also. This is like borrow or carry. Tell me, this expression is looking like a borrow. Okay, here this will perform A minus B. Okay, so this will perform B minus Q or Q minus P. How to justify? Compare, just compare. We have done this yesterday na, for A minus B. We have subtracted from A and B. Okay, so where you have bar in the expression, just compare that. Where you have bar, that is the operation. So what is the answer? B minus Q. So it is a subtractor circuit. Each one is one full subtractor. Each box is one full subtractor, which will perform your difference and borrow of P minus Q. Okay, so 4 are cascaded. It is a 4-bit subtractor giving P minus Q, not Q minus P. Is it clear? Yeah, initial one is 0. That's all. So please understand, yesterday class, Nidhi, you attended yesterday class, I hope. Yes or no? Please tell me first that. Yes, please listen here. Please listen here. Your data contains only two R, P and Q only. There is no R at all. It is doing 4-bit operation of P minus Q, two 4-bit numbers only. You don't have third 4-bit number. You have two 4-bit numbers, P and Q. Okay. So Nidhi, please ask your doubt. If anyone have a doubt, please understand first. Everybody understand it is subtractor, yes or no? Everybody accepted as subtractor or not? It's not adder, subtractor. And now see where you have bar, that minus other. Simple rule. Where you have bar, that minus other. Clear? Earlier it is a bar b x. You should remember these expressions. A bar b plus a bar c plus bc is a minus b. So compare with that. B bar q, b bar r q is p minus q. That's all. Now listen. Now listen. In the computer, you don't have separate circuit like this for adder and separate circuit like this for subtractor. Okay, computer hardware should be minimized as maximum as possible. You should minimize the circuit. Okay, please understand. We should try to do in the computer subtraction with the help of addition only. That we studied very well in the number systems. Yes or no? In computer, Ganesh, I think you asked me earlier. Now your signed method is coming. Just see. In computer, a minus b is performed by a plus 2's complement of b. That is, we should have only one circuit. We should have only one circuit which will perform both addition and subtraction. We should have only one circuit which will perform both addition and subtraction. How it will do? See here. If you want to do addition, it will do a plus b. If you want to do subtraction, it will do a plus 2's complement of b. That is, here only this part is to be changed. Circuit is the same adder circuit. It will save my hardware. Okay, so this is what we call universal adder and subtractor circuit. Okay, that is what we are going to discuss now. Universal adder and subtractor. That is the same circuit which will perform both addition and subtraction. The same circuit which will perform both addition and subtraction. What happened? 1 minute, please. Yeah. So earlier I took some screenshot. It helped me to save our time dynamically. So let me design the circuit of both adder and subtractor. A3, A2, A1, A0. So here I use one gate, what we call XOR gate, which can help to make the complement of the number. This is A3. Sister carry locate address not yet discussed. That will come next, maybe today only. Yeah. Just wait for some time. I will discuss carry look ahead address not yet discussed. Okay. Listen, I hope you know this basic. I hope you know it already. What is B XOR with 0? Comment B XOR 0 is if other input is 0, you get 0. Other input is 1, you get 1. Why different answers are coming? It is B only. If B XOR with 1, what is the answer? B bar. Okay, after discussing the next topics, you should not miss the basics, man. Okay, so listen here. You take this as some control input that will decide whether you need to do addition or subtraction. So first, let me explain for addition. When control equal to 0, okay, it will perform addition. I will prove it. When control equal to 1, it will perform subtraction. So first I will start control equal to 0. Then what will I get here? 0. And one of the input to the XOR gate will be 0. If one of the input to the XOR gate is 0, what is the output you will be getting is the other input as it is. Okay, then when control equal to 0, it is adding A3, A2, A1, A0 with B3, B2, B1, B0. It will do addition of this, that is nothing but A plus B, normal addition only. So that will give you your sum, carry, sum, carry, sum, carry, and sum, your carry. Is it okay? Is it okay up to this? Now the main part. Now the main part. Listen. If control equal to 1, agar control is equal to 1, what happens? So here you give 1, here you give 1, here you give 1, here you give 1. So if you give one of the input to the XOR gate, it will give you complement B3 bar. What is this? B2 bar, B1 bar, and B0 bar. Now, when control equal to 1, your A is as it is, A3, A2, A1, A0. Okay. And what is B3 bar, B2 bar, B1 bar, B0 bar, and also your C0 is how much? Tell me, C0 is how much? You see here, it is A plus B bar plus 1. What is B bar plus 1? Tell me. That is A plus 2's complement of B. That will give you A minus B, which is giving you subtraction. Okay, so take the number V3 may 1010, it will complement as 0101, and at LSB it is adding 1 bit again. That will give you 2's complement. This is how you can perform subtraction here. Ganesh is there, he asked me doubt earlier, he is there or not? What is your doubt, Abhinit? Please ask. C naught. Okay, please see here. How to perform 2's complement? Please listen. You have 1010. What is 2's complement of 1010? 0101 plus 1. Na? Abhinit. Okay, I am saying the same thing. Please see. Is it yes or no? Same way. Here, whatever. Okay, now see here. We take 1's complement. This XOR gate will do plus 1's complement plus 1. For that, you should have this C0 compulsory. That C0 will be given as 1 here. This is your C0 now. Control is the name we have given. You can give your name Rahul. Okay, it is just your name. When Rahul is equal to 0, it will do this circuit will do addition. When Rahul is equal to 1, it will do subtraction. Just control is your name. When control is 0, this line is this line name, I keep it as control. Okay, you can keep it any name, no problem. If its name is, if it is 0, it is performing addition. If it is 1, it is performing subtraction. Why C1, C2, man? You want Swapnil? Why after this you forget number system? How to make 2's complement of this? Take first 1's complement 0, 1, 0, 1 and add 1 only here or every place? We add only 1 here. Then if carry comes or not, accordingly this adder will take care of it. 1's complement plus 1 is 2's complement. Yes or no? This is LSB for your understanding. This is LSB and this is MSB. Okay, fine. This is what we call universal adder and subtractor circuit, which can perform both addition and subtraction. In the system, you may use for a direct addition this kind of circuit. You may not be using this. You may be using efficient algorithms to perform the addition, but generally, I'm saying. Yes, Nishita. Okay, Kalimbai, no problem. Okay, why carry equal to 1 for subtraction? To make 2's complement. Is it fine? Let's move further. So get ready, guys. Next one, please see this. Consider the circuit in the figure which has, please get ready with your answers. 1 minute. We'll do this later. Otherwise, one more question is there. Let me do. That is not loaded. Leave it. Okay. Then it will do reverse job. AD, that's all. It may do addition for this 1 and subtraction for 0. That's all. Okay. Now, I have 2 points to discuss. Which one I want to discuss? Let me start BCD adder. Then I will go for carry look at adder also. So let me design the next one. What is that? The next one is I want to discuss is BCD adder. Right, Asif? Correct, exactly. Yeah. You need one inverter also in that case. Yeah, binary coded decimal BCD adders. So job of this BCD adder we are designing is we have, where is that Ganesh is not there? He asked me earlier. So people are like that. They come randomly, they go randomly, but you are there. Reset and clear. So your doubt is cleared, Ganesh. What happened here? You are not commenting. Baba Ramdev joined. Oh, very good. Let's ask some Patanjali products, please. Corona vaccine available. Okay. So listen. BCD adder. What is the aim of this BCD adder? Don't deviate here. Okay, once your joke is done, come back to class. Okay, don't do analysis of your axiom now. Okay, what is that? We have a binary adder, but it should perform the addition of two BCD numbers. BCD adder is to perform addition of two BCD numbers using binary adder. As earlier, some people also asked, binary adder don't know what is the input you are giving. You should do these modifications to perform your job. Like here, you have done this modification to make 2's complement addition. Similarly, that adder circuit is same. It will do blindly addition. You give inputs to that such that it will perform BCD addition. What is the difference between this BCD addition and binary addition, sir? Let's see. First, your aim is it clear, your aim? Your aim is to perform the addition of two BCD numbers using a binary adder. Okay, so now listen here. You have a number A. Okay, it's a BCD number A. Let me give you some basics. Okay, BCD number A, which is 4-bit. 4-bit BCD number A can be range. Range is how much? 0 to 9. Okay, another 4-bit number. Another 4-bit BCD number B. What is the range of it? 0 to 9. So if you add A plus B, what is the range? You add 0 to 9 and 0 to 9. What is the answer range? Why 0 to 9 here? Add A plus B, add 0 plus 0, 0 plus 1 plus 1, 0 plus 9. What is the range of this addition? What is the result? Okay, you say result range. Result range is 0 to 18. 1, 8. Very good, very good. So this is what you understand here. Please see. If it is 0 to 9, your result I am speaking. If result is 0 to 9, okay, it depends on the input. Now 0 plus 2 can be added, 1 plus 2, 3 plus 4, 5 plus 6, any numbers can be added. So if your result is in the range of 0 to 9, BCD and binary result by इसका मीन क्या? Same. Okay, 4-bit only, 4-bit. So during 0 to 9, that is you add 3 and 4 here. 3 means 0 0 1 1. 4 means 0 1 0 0. Add karne, what is the result after that? 7. Whether you do it by BCD or binary, doesn't matter, result same now. So in this case, I need not worry. I need to worry when result greater than 9. This point clear, everybody? During this period, the adder, don't worry about it. Okay. Now, sir, how adder knows it? That is your job. What we do? Okay. If result greater than 9, okay, if result greater than 9, then what to do? Already we have discussed in the number systems happily. Here also we discuss. Then binary result, just listen first. Binary result is 1001. My BCD result should be 1. Okay, suppose not 9. Let me take greater than 9. No? So 10 is your answer. 10 means 1010 in the binary. But for the BCD, why are you worrying about that adding 6 here? Let me derive that. Today your people are behaving differently. I don't know why the reason. So you need 1 all zeros. Why you need to add 6? Why? Tell me, those who comment 6 now, tell me why we need to add 6. What happened? No comments are there. Why 6 only? Why not 5? Why not 4? Why not 3? I am asking why not 4, 3, 2 something. Okay. Yes, Aditya, I will say later. I said, okay. Listen. Then why you people are commenting? You should. This point is to learn, right? So result is 16. Result is 16. Please listen. Result is 16 means this much. Okay, but your BCD result is 6. BCD result is Prakash, you can say like that also. 6. Sorry, BCD result is how much? 16 means 1 separately, 6 separately. Yes or no? 1 you should write separately and 6 you should write separately. This is 6. This is 1. Similarly, your result is 18. I am taking all possibilities. If your result is 18, in the binary, 18 will be like this. But in the BCD, what is 18? 1 separately, 8 separately, you should write. I am giving you logic. Okay, we can design directly by blindly saying you should add 6. That is not the intention. You should know how it is coming, why it is coming. This is 1 and 0. This is BCD representation. So your job is, please understand your job. Our aim is to convert this result into this result. Your adder will do this job. Adder happily do this without saying anything. Give input to the adder. This will do this job. Because it don't know now you are giving BCD or binary. It will do its job. Your job is, when it is 0 to 9, keep it as it is. When it is more than 9, you should make it like this. You should convert like this. Okay, your job in the sense, you need to design. We need to design a circuit which will perform this operation. We need to design a circuit which will perform this operation. For this operation, first you should check what is the relations are here. What is the relation between this and this? What is the relation between this and this? All the cases, what is there any common relation? We need to check that. Okay, you see here, this 16 is here. What is the understanding you can say is, you see these two. Okay, 1 all zeros minus 1 0 1 0. What is the difference between these two results? What is the difference between these two results? If you calculate, it will be 6. Similarly here also, what is the difference between 1 1 0 0 and 1 0 0 1 0? How? What is the difference here? It will come out to be 6 undoubtedly. So this is the reason, because the difference is 6 Hamesha, every time the difference here is 6, we are adding 6. Okay, so by subtracting these two, you understand that every time the difference is 6. So now, if result is greater than 9, I add 6. 6 means how much? 1 1 0 binary. Is this clear, this point now, everybody? The logic behind that. So for example, okay, 10 is there. What is 10? 1 0 1 0. Add 6. What will you get? 0 1 plus 1 sum 0 carry 1 1 plus 1 sum 0 carry 1 1 plus 1 sum 0 carry 1. Okay, so that will make your result. What is the question, Aditya? If the result is in range, which range? Result is 0 to 9, it is same, no difference. 0 is the difference. Similarly, for example, your answer is 18. In the binary, what is 18? This one. So add 6 here. So 1 plus 1, sum 0, carry 1, 1 plus 1, sum 0, carry 1, and this one, and you take this one here. Okay. So this is 1. One minute, I'm sorry. And this will be 8. Okay. Right. Fine. You understand. Now come to implementation. How to design this? Let's see. First you take binary result. Okay. S3, S2, S1, S0, and carry C4. So when binary result is 0 to 9, please understand, when binary result is 0 to 9, what about BCD result? You understand, your aim is to convert a binary result into BCD result. It is same. Okay, as binary. Okay, so you can write like this. It is same as binary, that is all zeros to 1 0 0. Up to 9, they will come as it is. Okay, I'm sorry. Up to 9, they are same. That is the same. Okay, when your result is greater than 9, now comes your original. When result is greater than 9, that is for 10, 11, 14, 12, 13, 14, 15, 16, 17, 18. All these cases, what is the answer? Here, 10 is 1, all zeros. 15 should be written as 1 and 5. 16 should be written as 1 and 6. 17 should be written as 1 and 7. 18 should be written as 1 and 8. Okay, so in this case, what to do? Add 6. When to add 6? If I ask you, simply you can say like this. Now listen here. Okay, I want to give you one point. Please listen. When to add 6 is, in these all cases you add 6. Can I write the statement like this? Please listen. Okay, if sum greater than 9 or carry equal to 1, add 6. Result greater than 9. What is the meaning of result greater than 9? What is the meaning of result greater than 9? Your sum may be greater than 9 or carry may be 1. You should see both the cases. Na? Some 4-bit, if you see only this part, it may look like 2 only, but you should check carry also. That's why I am saying whether your sum may be greater than 9 or carry may be 1. Any one of this condition is satisfied, add 6. Is it clear to everybody? Then I will proceed. Otherwise, I will clear it and proceed. Please ask. We have only 4 bits. Don't worry about nibble and all. We have only 4 bits here. Earlier we discussed 8 bit. That is a different case in the BCD adder addition. Here only 4 bits, man. No nibble concept or no auxiliary carry. You have only one thing here. What is your doubt, people? Please ask. If you have doubt, please ask me clearly where you have the doubt. There I can stress more. Last observation, Vivek, see here, all during this period, result greater than 9. How computer will see this? For computer, you should say result greater than 9 can be done by this part. This part is called sum, na? This part is called carry. Sum may be more than 9. Okay, everything we are doing in binary only. Please understand. Your adder is binary adder. Your design binary adder, you are using it for BCD. Now please listen. Okay, Vivek, see. If this is greater than 9 or carry is 1, any one of these condition is satisfied. In all these cases, you should add 6 to get the valid answer. Vivek, clear? And Pupul, is it clear now or ask me again? Okay, fine. So, very good. So just listen. I will write this point so that when you download the notes, it will be good. Okay. So when we add two BCD numbers, using binary adder to get a valid carry only. It is not signed operation, Navicha. To get a valid BCD result, okay, first we need to perform following. If result 0 to 9, it is same. Second, if result greater than 9, that is sum greater than 9 or carry equal to 1. Only for signed operation we may not. We will get we make it as overflow. We treat it as overflow in the signed operation. Otherwise, we treat it as carry. That we discussed in the number systems already. If result greater than 9, that is sum greater than 9 or carry equal to 1. Okay, we need to add 6 to the result. Make a note, very important. When we add 6, always, when we add 6, always carry in BCD result is equal to 1. Keep this point. What, sir, what is the meaning of this? Just go back. You are adding 6 in all these cases. What is the carry in the BCD result? Everybody observe it. Sir, why you specifically saying this, sir? What is the importance of this? Go back. Go back. Here you observe. You added these 4 bits now. Here you added these 4 bits. It generated carry here. But here it no carry is generated. I just take previous carry here to get the answer. You observe this difference is in this edition, this 6 is added now. This 1 plus 1 give me 0 and carry is generated here for 4-bit addition. But here this addition is not generating any carry, but I have taken previous carry here. You observed this or not? Here I took 4 bits only, here I take 5 bits only. What is this? This is your carry, this is your S3, S2, S1, S0. Here that 5th bit is taken as it is. You observe this both the cases, yes or no? Tell me please. So please listen. This addition of 6 may not give you carry, but you should take the carry always to get the valid answer. So this addition may or may not give, don't worry, blindly carry is equal to 1 in all the, whenever you add 6, carry is always 1 in the BCD result, because the answer is greater than 9. Is this point clear to everybody? Okay, so how you implement, don't worry Rishi, just wait. First point is clear or not? Okay, so now let's implement this. Listen here. Let me make one K-map. A, B and CD. If sum is greater than 9. So sum na, so instead of ABCD, for your better clarity, I will take it as S3, S2, S1, S0. If it is greater than 9, what is the meaning of greater than 9? 10, 11, 12, 13, 14, 15. So you can make quad or not. Two quads are possible. So what is your answer? For this K-map, it is S3, S2 plus S3, S1. This K-map is telling my sum is greater than 9. Okay. Now I add one more thing. Okay, what is that? R carry equal to 1. Okay, R means plus, if carry equal to 1. In this case, you need to add 6. Is this point clear? See here, when to add 6, result greater than 1. What is that? Sum greater than 9 or carry equal to 1. This equation will tell you sum greater than 1, so sum greater than 9, or R means plus, carry equal to 1. Okay, if this equation is satisfied, add 6. Is this point clear to everybody? Then I will move further. Everybody. Now let's design this. So let me take a 4-bit parallel ladder. Another 4-bit parallel ladder. Please understand, I can explain directly from this figure also, but it will not give you the real feel of how you are going to design. Okay. A3. We should have the design. How to design, we should know. Why it is not necessary, Aditya? If here sum is not greater than 9, how will you add 6 here for this last 3 cases? Aditya, please tell me. Last 3 cases, how do you add 6? How will you check? Only 4 bits you checked. It is not greater than 9. But to add 6, you should check another condition. What is that? Carry equal to 1. Okay, Aditya. What happened here? No comments. Sum greater than, please listen. If how you represent 16? Yes. Yes, Asif told correctly. How? What is the answer for 16? Both of us got the same number. 16 means 1 followed by all zeros. It is greater than 9 only, but some will not say it is greater than 9. Carry will tell that. So the information is in 2 of them. Any one of them will tell you whether it is greater than 9 or not. Okay. Yes, result greater than 9. Either sum may be greater than 9 or carry equal to 1. Both to be taken. Adhika, is it clear? Okay, let's move. So here I will give my BCD numbers A3, A2, A1, A0 and B3, B2, B1, B0. These are your BCD inputs. Okay, here no C0 is required. Okay, now please listen. You will get here sum S3, S2, S1, S0. Expression. What is your expression, man? S3, S2 plus S3, S1. So take here one OR gate which will do the operation of S3 into S2 and S3 into S1. So take one AND gate, another AND gate, and also carry na. So three of them you give it to OR gate. So now please listen. This is the logic of S3, S2 plus S3, S1 or carry equal to 1, add 6. So when this logic is true, what you need to do? What you need to do? Add 6. How to add 6, sir? Simple logic. Please listen carefully. How to add 6? If it is not true, add 0. If it is true, add 6. That is done like this. Ground. This is also ground. If you are CSC, simply write it as 0. No problem. Okay. So now these two bits you connect like this. Okay. Now you observe. It is permanently 0. This is permanently 0. This is also permanently 0. What about the middle one, sir? If this logic is false, it will not add anything. If logic is not true, it will not add anything. So result will be taken as it is. Result will be taken as it is. Result will be taken as it is. Okay. If logic is correct, then what it will give here 1 and here 1. Then 0, 110 means how much? 6. So now, right. It will add 6 in this case. So now one twist, I left it for you. I need answer from you only. S3, S2, S1, S0. No, I am not right here. I didn't invent anything. I just explained you the logic. That's all. Now onwards, because of this, you will be able to design anything. That is my intention. So now please tell me, for BCD result, how to take the carry? I told you now, in the BCD result, when you add 6, it should be always 1. When you don't add 6, it should be 0. Thank you, Akshat. Please tell me what to do. This logic you should say. I cannot take this carry. I already told you now. When you add this, carry may or may not generate. Okay, I already told you this example also. Yes or no? Carry or may not generate. Always you should take carry 1. Whenever you add 6. Whenever this is 1, you should take carry 1. Whenever this is 0, you take carry 0. Instead of, okay, for that, can I say like this? Why to take another logic? Directly take this fellow as your carry. Here already, you take himself as your carry. So this will be your BCD result. Okay, why to make a no need to have any logic? If this is logic is 0, carry 0. Logic is 1, carry is 1. That's all. Yes, right, G. Okay, you need not take this one. Okay, this is of no use for us here. This is what we call design of BCD adder. Okay, so any kind of doubt, please ask me. Otherwise, we can move further. If number is 9, nothing will be added. Number greater than 9, that is from 10 only it will add. Yeah, for up to 9 carries 0 only. You see here table. Up to 9, what is your carry? 0. For after 9 only this carry will be 1. So आगे चलेगा. Let's move further. Even 99% of the class says yes. Even you have doubt, ask. Okay, please don't hesitate. Out of the 100 people, 99% understand, 1% don't understand. You ask me. Okay, everybody saying yes. So, why can't I ask? Don't think like that. What is Aricha? How did you take carry? This one. Whatever you, whenever you are adding 6, this is 1. That is your carry. Okay. What for poll? You are open to comment. Okay. So I already told you, whenever you are adding 6, when you add 6 every time take 1. Okay. When you add 6 carry 1, don't add 6 carry 0. That's what I meant. Okay. When I add 6 carry will be 1. No, not adding 6, no. Okay, fine. No, Rohit, I am saying that they should not hesitate to give the answer in poll, hiding their faces. That is not the good habit. I want everybody to comment live, because in the poll, your face will not be, I mean, not used. Generally, people face will not be available, name will not be available, so they may be free. My intention in the class, they should feel free to comment. If we habituate the poll every time, they will be waiting for the. So listen next. So tell me this answer. I'll conduct the poll. Just give a reading of this. Consider the circuit shown in the figure, which has a 4-bit binary number. What happened here? Binary number 3. This is binary. Okay. Number B3, B2, B1, B0. Okay. This is the number B3, B2, B1, B0. As input, and a 5-bit binary number D4, D3. See, D4, D3, D2, D1, D0 as output. The circuit is implementing what? You see, this is 0. You are adding here for these 3 0. For this, you are adding 1 or 0 depending on this logic is true. Okay, it is similar to previous case. So what he is asking is what it is doing. Binary to BCD, binary to hex, binary to gray code, or binary to radix 12 or base 12. Shall I start the poll? Now, after this question, previous case, you will be able to answer this easily, I think. I will explain little more. When both are ones, it is adding 4. When B3, B2 both are ones, AND gate will add 1 here. 0, 1, 0, is 4. Okay, write this point. Then you answer at least. B3, B2 equal to 1, 1. Then add 0, 1, 0. Otherwise, add 0, 0, 0. So if you write the numbers 0, 0, 0, 0, 0, 0, 0, 1, I want everybody to answer. So little explanation I am giving. 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. These are your numbers. Okay. So in these cases, it is adding 6. This adding not 6, 4. This much explanation I am giving and conducting the poll. My dear friends, get ready. Tell me the answer. I forgot to tell you, sorry, forget to provide you one key for one DPP, last DPP. Now, tomorrow I'll provide another DPP also. Yeah, half almost I solved it, Ganesh. Suraj, Deepanjali, Arun, Mohan, Ashish, Asif, Aman, Vivek, Sagar, Manjunath, the right answers. So the answer is binary to base 12 conversion. Listen here. In the base 12, if it is 0 to 11, it is the same. Okay. For 12, it is represented as 1, 0. 13 is represented as 1, 1. 14 is represented, as 1, 2. Okay. So 1, 0 means it is a, for BCD representation, it is 1 followed by 4 zeros. What happened? Option is not available, not visible. Now come to the question. Everybody see here. When B3, B2 both are ones, there will be 1 coming here and 0, 1, 0, 4 will be added. When B3, B2 are 1, 1, they will add 4. Why add 4? Earlier, like add 6, here it is adding 4. Okay. So when 12, 13, 14, 15 comes, they are adding 4. So 1, 1, 0, plus 4. What is the answer? It will give you 1 and all zeros. Like that for whatever you have 15, they will add 4. You will get 1 and 5. Like that they are doing. Okay. So please understand. So up to 11 as it is, for 12 onwards, they are adding 4 to get this. So what is this conversion? Binary to radix 12. Not binary coded decimal. It is not decimal here. Decimal may you take only 0 to 9. Here it is taking 0 to 11. Is it okay? Okay, fine, fine. Very good. So let's move further. Next, your favorite is coming. You are asking from long time. Yeah, we'll do more questions. Let me complete this part mainly. Carry, look ahead at. The next one. This is important. What is that? Carry, look ahead at. Okay. Earlier, what is the disadvantage in your binary adder? Delay increases with increase in the number of bits. So what happened, Rahul? In the BCD, listen, Rahul, 0 to 9 as it is. When it is 10, that is 1, 0, 1, 0. You write it as 1 all zeros. Similarly, here, what he is doing for 0 to 11. Same. When 12 comes, he is writing as 1 followed by all zeros. That is 1, 0. You know, 1, 0 represents the base of the number system. Okay, or it is up to 11 as it is. For 12, it is represented as 1, 0. Okay, fine. So let's move. So in the, what is the advantage of carry look at address? It will generate carry at every stage without depending on the previous carries. It will not, because it is depending on previous carry. In the ripple carry, delay increased. That disadvantage this fellow will overcome. He will overcome the disadvantage by generating the carry individually at each and every stage. At each and every stage, he will generate it individually. Let's see. Okay. So firstly, for your understanding, carry logic. Okay. When the carry comes, when the carry don't comes, let me have that analysis. A and B. So 0, 0. When A and B are 0, 0, your carry input is 0. Our carry input can be 1. Two cases are there now. What is the answer here? Some 0, no carry. Some 1, no carry. So what is the carry output in both the cases? 0. This is the case what we call no carry. Is it okay? You are accepting? When A and B are 0, 0, you need not worry about the carry input. It can be anything. You will not get the carry in the next case. This is carry coming from the previous. This is carry going to the next. So you understand this. When A and B are 0, 0, carry input can be 1 or 0. Doesn't matter. It will not give any carry to the next state. Is it okay? Then I will proceed further. This will tell that next is you need not depend on me because my carry input can be anything. I don't give any carry. Okay. So next. Your AB can be 0, 0 or you can take 0, 1 also, 1, 0 also. So now if carry input is 0, two cases I am taking, analyzing, just analyzing two possibilities. Right. Both the cases I am taking. Now tell me what is the answer here. All zeros plus 1. Sum 1, no carry. 1 plus 1, sum 0, carry is there. Now, okay, just wait. Leave it for some time. You take AB, both are 1s. You take this as your carry input, this as your carry input. Two possibilities are there. Okay, fine. Now what is the answer? Sum 0, carry 1, sum 1, carry 1. Everybody up to this clear? Normal addition only. Okay. Now I am going to derive one thing. Whatever here, whatever the carry input, if it is 0, you get 0. If it is 1, you are getting 1. What does it mean? What is the conclusion you can say? When AB are 0, 1, 0, 0, no carry. When AB is 0, 1 or 1, 0, if you have carry input, you will get it. If you don't have, you don't get. If you have, you get. We call this as propagate carry. What is the name of this condition? We call propagate carry. If you have here, it will come. If you don't have, it will not come. But what about this? Here, it does not depend on the input carry. Carry can be anything in the input. It will always give. This is called generate carry. What is the name of this? Generate carry. Carry will compulsory generate here irrespective of your input, carry input. This is happens when A and B both are ones. Now I will write it as A into B. This is given by some variable G you take. When this G occurs, when A, B both are same, both are ones. When this occurs, when propagate carry occurs, when A, B are 0, 1 or 1, 0, you can write A XOR B. When different, when both are different, you can say. When both are not same, both are ones, you will get this. So up to this clear to everybody or not? Tell me. When AB 0, 0, carry input can be anything, no carry will come. When AB 0, 1, carry input 0, you get 0. Carry input 1, you get 1. We call it as a name propagate carry, which is happens when AB are different. When AB 1, 1, if there is no carry or whether carry is there, both the cases you get carry. Okay, this is what we call generate carry. So finally, when can I get carry? That is the question. When can I get the carry in the output? You can say like this. Generate carry should occur. Generate carry should occur. R means plus. Propagate carry with carry input equal to 1. Can I write the expression like this? Generate carry A and B both should be 1 or both different with Cn equal to 1. Either this condition or this condition is true, you get the carry. Everybody happy or not? Accepted. Then what is your Ci plus 1? What is the carry in the next state? Carry in the next state is just name changed. If it is C out, in place of that I keep Ci plus 1. It is a Gi plus Pi into Ci. Gi plus Pi into Ci. Okay. Now you can write what is Gi? Ai Bi plus Pi. Ai XOR with Bi into Ci. You remember this is nothing but your expression for carry in the full ladder. AB plus A XOR B into C. Yes or no? And if you solve this equation by K-map, you can also say it is equal to AB plus BC plus AC. That can be written as A plus B into C. After minimization by K-map, you can say this will convert into this. I am not saying XOR will become plus. Okay, after take this equation, minimize it by K-map or Boolean algebra, then you will get back this equation. So in some textbooks, propagate carry is given as XORs. In some textbooks, propagate is also given as A plus. Both are correct. Okay, because after minimization this expression will come back as this expression. So in place of XOR, if you take OR gate also, it will work properly. So different textbooks will follow different terminology. So don't worry about your exam. I will show you what to do in the exam. Okay, is it clear? In the place of propagate, some people will take XOR, some people will take OR gate. Both are correct. Yeah, that's all. But in a systematic way, you can write like this. Yeah, it is AB plus BC plus AC only. But we write it in a different way to get a clear picture now. Because this is the basic required for carry locate adder. This is the basic required for your carry locate adder. Today I will take little more time of you because I told yesterday also. Actually, because I want to complete this part, just to figure if I complete, then it will give you better picture. So let me complete this. It is a continuation. That's why. So let's move further. So what is your Pi is equal to Ai XOR with A. Your sum is nothing but Gi, because A XOR B is Pi, Pi XOR Ci will give you some. Let me make 3-bit carry located, because in the available screen, because the design is same. Let me generate a 3-bit generator. 4-bit also, I will extend it. Once you get for 3-bit, 4. What is C1? What is carry in the first stage will be equal to G naught plus, tell me, P naught C naught. Otherwise, what is the carry in the second stage? Please tell me. G1 plus, tell me, I will not proceed further. That is your problem earlier. Now what you do? What you do, if you take like that, it is normal adder. What you do is here you take this C1 again. C1 you substitute here. G1 plus P1 G naught plus P1 P naught C naught. Is it okay? I just substituted this C1 in this. Can you tell me what is C3? G2 plus P2 C2. That is G2 plus P2 into this whole equation. What is that? G1 P2 into P1 G naught P2 P1 P naught C naught. Like that you can extend the expression. Now, so what is your C1? It is G naught plus P naught C naught. What is C2? G1 plus P1 G naught plus P1 P naught C naught. What is C3? Okay, Asif. I think you understand your time is up. Trying to write. Good evening, Kumari. Yes, it is working. Okay, fine. So listen here. What is C3? It is G2 plus P2 G1, P2 P1 G0, P2 P1 P0 C. Okay, so these expressions I got it here, I copied as it is, nothing great. Now listen. Now let's make this carry generator circuit. Listen please. This is carry generator circuit. Okay, now please listen. You give here the C0, you will get here C0. What is C0, sir? Initial carry. Then you give A0 and B0 to one AND gate. What you get it here is G0 gate. Very good, very good. What you get it is P. Similarly, you take A1, B1, you give it to AND gate. What you get it is, and you give it to XOR gate. What you get it is P2. Okay, now see what is your C1 G0 plus P0 C0, that is G0 plus P0 C0. For that you take one AND gate here, and from them you take one OR gate. Now this will make C0. What is that? C1 P0 P1 P0 C0. There are some questions based on this figure, that's why I'm taking extra care to draw this. Okay, please listen here. You need not remember it, but please understand that. Next, late Khalil. Okay, you ask me when you attend for the full class, I can say already it is done. Done or not, if you come in the middle, you cannot say whether we have discussed it. Right, in 3-bit you get. Okay, done. Your figure is done. Please listen here. Here you take one XOR gate, you get the sum S0, and you take another XOR gate. 1 minute. Okay, please listen. Why I take P naught XOR with the C naught is S naught, P1 XOR with the C1 is S1, P2 XOR with the C2 is S2, and finally you get the carry. We have added 3 bits. Now calculate the total delay. Calculate the total delay. What is the total delay here? These two are parallelly acting. Now assume one gate is 1 TG, 1 TG or TPD, your wish, no problem. So here how much delay? 1 and 2. So how much? 2 TC. So up to this point, it is having 3 delays. Now for carry 3 delays, and here, what is that? One more delay, na? Total will give you 4 delays. Now you understand one important thing here. Please listen. Your sum requires 4 gate delays. Carry requires 3 gate delays. What is TG here? It is a gate delay. 1 gate ka delay now is TG. Okay, so please listen here. Now, if I make a 4-bit adder, what happens? Here will expand vertically or horizontally. I take a 4-bit adder, then some part will come in the bottom or right side. Yes. So if you make a 4-bit adder, then it will come again vertically, not in horizontally. What does it mean? If you increase the number of bits, you require more hardware, no doubt in it, but delay will not increase. Delay remains the same. So your number of gates may increase, number of inputs may increase, the circuit complexity will be increased. Definitely hardware required more here, no doubt, but delay will not be increased. Here n and delay are not related to each other. N is already here, delay is fixed. It is independent of n. Yes, GP, that's what I said. Now hardware requirement will increase, but not the delay. Hardware requirement is increased, definitely more number of gates are required. So if you have limitation to number of inputs, then you may be using 1 gate may be implemented like that. In that case, delay may increase also. Yes, Sushil, that's what I made now. P XOR not C, not G. P XOR G is not C here. A XOR B XOR C. What is A XOR B is P. C is this one. Why it is G XOR B? Sum is A XOR B XOR C. Okay, fine. Now listen here. One important objective bit. I will leave you just 5 minutes. Okay. Number of carry generator circuit. Only in the generator circuit, how many OR gates are used? Only in this part, not outside and this side. Here only how many are used? Can you say n? N, where n is the number of bits. Okay. Then what is the answer for number of AND gates? In how many AND gates? 1 plus 2 plus 3. I can say it is n into n plus 1 by 2 is the formula, because sum of n natural numbers. Sorry, first n natural numbers, because 1, 2, 3. If you have 4 more gates will come. Okay, so this is the generalized formula which you should remember. And your doubt. What is your doubt? Sushil, last formula about number of gates in this. What is the number of AND gates here? 1 plus 2 plus 3. If you have one more, you get plus 4, plus 5, plus 6. 4 times each gate delay. 4 times 1 gate delay. 1 gate delay is TG, then it is 4 times gate delay, because it is going through 1, 2, 3, 4 levels. Aditya? This 4 is, there is no n here, na? There is no n here. Okay. Here TG is 1 gate delay. So 1, 2, 3, 4. 4 gate delays is required. It is not depending on n. N can be any number of bits. Your answer will be same. That is the advantage here. Earlier your answer is n minus 1 into TC. Something is there. If there n increases, delay increases. Here the disadvantage is not there. Just give these answers fastly. We can leave the class. Tell me the answer. Get ready. I will start the poll. Just so you don't afraid with this now. You can answer it easily now. After our explanation, you can answer it very easily. Everybody in the class is able to answer it. Just read it. function pi or the inputs ai are given by, see all this story you know it only. This XOR Ci is a Gi plus Pi Ci, C naught is the carry. All this story is same. I don't understand what is your doubt. Why not using C1 for C2 directly? If you use C1, this story becomes same, man. You take this C1 and connect it. Delay increases, na? This delay, again another adding delay. Okay. If that is there, it is same as ripple adder. You take this and add it here. Then delay increases, now you should wait for this and do this. Yeah. So assuming that all inputs are available, sorry, consider the two-level logic implementation. The look ahead carry generator, assume Pi, Gi are available, and OR gates can have the number, any number of inputs. Every point is important here. The number of, finally the question is here. Number of AND gates OR gates needed to implement the look ahead carry generator for 4-bit adder with S3, S2, S1, S0, and C4 respectively. Yes. So shall I start the poll? Ready? Very good. Almost most number of people giving right answer, 70%. Don't answer from the previous. I don't know, some people might not have studied for that. Please make your concentration properly. This is direct from the previous analysis. Number of OR gates is equal to n. Here n equal to 4. What is number of AND gates? N into n plus 1 by 2. That is 4 into 4 plus 1 by 2, which is 10. Here you add a question. Direct formula which is in the previous slide only. I don't know why you make mistake for this simple also. Don't mug up the results. Here your adder is 4-bit. Where is that? In a carry look at adder generator, wait means. It is a 4-bit. If you study the question with patience, your 2 marks is for you only. If you neglect the question, okay, 2 marks is not for you. It will take your another 0.6 marks also. So everybody happy with this result? It is very simply this much lengthy question you will be able to solve now. Lastly, answer this, we can leave. Lastly, answer this, we can leave. I'll start the poll. Arun, Mohan, Suraj, Asif, Ashish, Aman, Abhinay, Sagar, RK, and Deepanjali, right answers. So what is the right answer is here B, not E. The dynamic man, please understand the question properly. Listen here. That's why if you understand the circuit, no need to remember that circuit. No one asked you to draw this figure. That is not difficult also. So listen here. A 4-bit carry look ahead adder which adds to again the same story. 4-bit numbers is designed using which gates? AND gate, OR gate, NOT gate, NAND gate, NOR gate. Every gate is there for you. No, which gate is not available? Comment please. You are exhausted, I think. So just 2 minutes. XOR is not available. XOR is not available. Assuming all inputs are available in both complemented and uncomplemented form also, delay of each gate is 1 time unit. What is overall propagation delay of the whole adder? Implemented same 2-level AND OR logic only. XOR are not available. So please listen. XOR is equal to A bar B plus AB bar, which is equal to A plus B into A bar plus B bar. which is equal to AB whole bar into A plus B. I use this expression and I make AB whole bar. Okay. Here your job is not to find the gates. All gates are available. No need to make with NAND gate. You give AB here. What is this circuit? A XOR B. How much delay? What is the delay? 2 units. If you directly say XOR is available 1 unit only, but here 2 units. NAND requires one level, 2 level. Okay, someone saying 3. Why 3, man? For this one delay, for this another delay. These two work parallelly. Is it okay? So XOR requires 2 gate delays. Everybody accepted? Then your job is done. So listen here. You take here one XOR gate and one AND gate. And you have a logic of AND OR logic. At the output, you take another XOR gate. This is your story, na? You gave A, B, propagate carry, and another C, you get the sum. This is the block diagram. Yes or no? Now tell me how much delay. For XOR, 2 gate delays. For AND OR, 2 gate delays. Another XOR, 2 gate delays. Total answer requires how many? 6 gate delays. Why 4, Rishi? Not for carry. Total answer requires how many delays? 2 plus 2 plus 2. It is simply 6. So once you understand the concept, it is a 1 minute problem for you. Okay. So please listen. I am giving you one homework. 2 homeworks today I gave. Tomorrow I will do it. Okay. Try to do above problem with less than 6 delays. Actually, in the options, that answer is not there, but I am asking you to try this question with less than 6. Okay. According to option 6 is right answer, but I am giving you one homework to try this question by less than 6. Okay, same question, same statement, everything same. This only, in this statement only, X are not available. Okay, same statement, but I want less than 6. You try it and give me tomorrow. Tomorrow we discuss this and add a question 1 I have given. For that, if you want the answer, I can provide you. What is the answer? Where is that? Yeah. Homework I have given one question. Where is that? Yeah, answer is 50 nanoseconds. Answer only I am giving. Okay, to cross check your answers. That's all for today. So DPP will provide tomorrow onwards again for this new chapter. Tomorrow I will provide DPP and old DPP. I forgot to give you solutions. I will provide that also. So thank you very much. We'll meet tomorrow. This is for you. Okay, this you try today. So thank you very much. Good night. Good night. I will upload today. Please comment on the group. I will upload today. I forgot to do that. So thank you very much. Good night. Have a nice day.